In these sessions, I'd like to explain Eddington's model because this is standard model of stars. So in the standard models, we add the third equations, energy transfer equation in the models. So opacity is increasing with mass. So maybe I should draw the stars. So m is a mass inside of a spheres. With the increase of the mass, the surface of the spheres is moving outward. Then temperature is going to drop. Because of the decreasing temperatures, opacity is increasing. And also we need to consider the ietas. Ieta is a ratio between the F over M over L over capital M. Capital M is the total mass of a stars. And L is the luminosity of a stars from the surface of the stars. F is a flux, energy flux from the surface of a spheres. Mass becomes lowercase of the m. Total mass of the stars, actually this ietas becomes 1. L over capital M, this is a constant values. Also F is constant. If the nuclear reaction only happen in the cores, only the central regions, energy is produced. Then F is always constant and all the spheres. So F, L, capital M is constant. So this ieta is a function of the lower case of the m. So ieta is a decreasing function. If we multiply the increasing function of kappa times decreasing function of the ietas, we might have a constant functions. So if we multiply the kappa and the ietas, it becomes constant value. Actually, Eddington assumed that this should be the constant. Then we could perform the calculation. Kappa S, opacity at the surface. Kappa ieta becomes a kappa sub S, opacity at the surface. Then we'd like to find the radiation pressures. So in the last session, we derived these relations. Round P sub lat, round P equal to kappa F over 4 pi CGM. And then we have explained F over M is equal to the ietas L over M. So instead of the F over M, we use the ietas. Then you can move to the next line. Then we could use the assumption of the Eddington's models. Kappa ietas is a constant throughout a stars. So this is kappa sub S. So this is gonna be here. Then we could perform the integrals. This, if you consider this is the differential equations. P sub lat, radiation pressure is expressed L over 4 pi CGM kappa S P is the total pressures plus integration constant. Then we could use the boundary conditions. At the surface, pressures become 0. So radiation pressure and total pressure have to become 0. So from this integration constant is determined, is 0. C equals 0. So radiation pressures and the total pressure is related with these equations. So this equation says the constant ratio of the radiation pressure to total pressure throughout the stars. So P rad over this quantity is a constant. So we choose radiation pressure is a constant. So we choose the ratio is 1 minus beta. P is the total pressure. So this quantity we choose 1 minus beta. And the P gas pressures becomes a beta P. So if you add these two, P sub rad plus P gas, of course become the total pressure. ratio of the gas pressure and the radiation pressures with respect to the total pressure is a constant. We derived these relations. Then polytropic index we'd like to consider. So we have derived these equations. So if you express these equations, P total pressure is expressed as P radiation pressures divided 1 minus betas. Also from these equations, total pressure is P gas pressures divided by beta. Okay, using this should be equal. So this is the central part I proved. And the radiation pressures is expressed 1 over 380 to the 4th. This is equal to this one. And the gas pressures is expressed, this is the gas pressures. And then we can compare the most left hand side and the most right hand side to express T cube becomes 3 times 1 minus beta over beta k over a mu m sub h rho. So from these equations you can find these relations by taking the 1 over 3 power index. So from this equation you could find the pressures by substitute this T into the total pressures, because the total pressure is given by these equations. So total pressure is a P gas over betas. You can use this equation and substitute. Then it becomes expressed this one. It becomes a polytropic equations of the state of the index of the series, because this becomes a 4 over series. So index of the series. And this corresponds to the K. And also I derived when the gas pressures is expressed the polytropic equation of the state of the index series, unique relation between the K and M. So mass is expressed with the K's. So mass of the stars is expressed this ones. And as I explained, K is given by these equations. Then you can substitute this K into the here. Then equation relation between the beta and the M we discovered. This equation is quite difficult because the beta appears in the both sides of the equation. This is beta, and the beta to the 4th. And if we draw this equation as a function of the M over solar mass, so this corresponds to the mu squares M to the squares. If you consider the M is really small numbers, right hand side becomes really small, and its beta is 10 to the 1 because the left hand side has to become 0. So beta is nearly the 1. This means the pressure is mainly determined by gas. So gas is dominant. On the other hand, if you consider really heavy, this becomes a really big ones. To satisfy these equations, beta have to go to the 0. In these regions, radiation is dominant. So pressure is determined by radiations. For a restricted range of beta is differed from the unity 1 to the 0. And this range coincides with the range of the stellar mass, this region. So it's quite difficult to determine which gas and radiation, which one is more important. Actually, the inside of the stars, both gas pressure and radiation pressure, both are important. Then finally, the evolution of stars, we could describe the beta decreases as m increases. Radiation pressure becomes important for massive stars. So if you look at the massive stars, it's here. So if you consider really massive stars, radiation becomes dominant. This is the first. And the second conclusion is the luminosity is expressed as a power law of the mass of the stars. So from the radiation pressures over P, we discovered kappa SL over 4 pi CGM. So from these equations, and also that this left hand side is equal to 1 minus betas. So this equation, you can express the L. Here this equation. And also the 1 minus betas. I have derived these equations. Eddington Carty equations. Substitute back to the here. Then L becomes proportional to the m cubes. So luminosity is increasing with the mass of stars. So this relation is confirmed by observations. So theory was confirmed by observation. And the third conclusion, for a given mass, beta decreases with increasing. So for a given m, so we don't change the mass of the stars, but horizontal line is actually dependent on the mu. So if you increase the mu, pressure, actually radiation pressure becomes dominant. When the nuclear reactions occurs at the center of the stars, this means nuclear reactions formed a number of heavy elements. Because of the formation of the heavy element, mu is increasing. Mean molecular weight is increasing. So mu, if the mu is increasing, beta is decreasing. Beta is decreases. Beta, when the beta is decreasing, radiation pressure becomes dominant. So when the stars nuclear reaction is produce a number of heavy element, then radiation pressure dominant. Then some of the gas is going to escape from a stars. We observe that this as a stellar wind. Loss of a gas is observed as a stellar wind. Okay, this is the end of this session.